Better start then. Welcome everyone to the Astronomical Society of Edinburgh. It is a bit odd in here having a red light and so on, but we are astronomers, so we like red lights rather than white lights because it's better for observing, obviously. If you're a visitor, then very welcome, and make sure you speak to some of us afterwards as well. Don't go away without telling us who you are and so on. Good to meet you. We've got a really good full hall here. We've got members on Zoom as well. And we have visitors on YouTube as well, so you're all welcome. This is what we've got coming up tonight. My name is Mark Phillips. I'm the president of the Society. I've got a few news items just to fill you in what the Society's been doing, what talks we have coming up over the next couple of months. And then our main event of the evening is we have Dr. Stewart McKechnie here, who's an optical consultant, I think is your title, yeah, who's going to tell us about the star images and resolution of the European Extremely Large Telescope, another well-named telescope. I'll be doing What's in the Night Sky in February, and then we've got tea and coffee afterwards, so please do hang around and have a chat. And if you're on Zoom, time to mute your mic. Welcome to our latest new members. We've had quite a lot over the last month. So welcome to Chris, Malcolm, Mark, Aaron, Robert, Matthew, and Brian. I don't know if any of you are here, but can we welcome everyone as normal? Thank you. And our membership now stands at 213. That will drop very shortly because we're getting to February when, if you haven't paid your subscriptions yet, then Alan, the Grim Reaper, will be chopping you off the membership list. It is National Astronomy Week, so it's good to see so many of you here. That's 9 days of astronomy across the UK, the 1st to 9th of February, so we've had a lot going on. We did some outreach observing, which Andrew will tell you more about. Andrew did a test, a pop-up public observing in Portobello last week, and we got about 35 people, which is really amazing. I've been doing some live streaming on YouTube for National Astronomy Week, partly from my own observatory, partly from our remote observatory we have in Spain, Azero, and that's been going really well. Also, Pat Robertson and I did a bit of a pop-up observing session for our local neighbours as well, which was also successful. But last night was a bit different. Andrew organised another sort of pop-up observing event, and we got 200 people in Portobello, which was amazing, and Andrew will tell us a bit more about it.
Hi. It wasn't anticipated. After the success of last Wednesday, last Wednesday, I said about 35 people. We didn't advertise it. We didn't know what the response would be like. We didn't know what we'd be able to cope with. But it went down really well. We looked at the planets. Everybody thought it was marvellous. So I said, well, 3 full days, or 3 nights where it's going to be clear. We'll pick the middle one and we'll go for the moon. So I suggested to Catherine Haymans, the Astronomer Royal, and Andy Lawrence, who happened to live in Portobello, that we go back to Portobello. Yes, they said. Surprise, surprise. So we did. And Catherine said, I've just let the local primary school know. And it went out on the bulletin, and at least 200 people rocked up. Very, very patient. I'm very grateful to those that turned up. We had 3 large dobs. I think there was a 10, 12, I don't know what Paul's was, probably a 14, but at least it was on a trolley. And Mike and Catherine and Tim brought sea stars. And we started at 7:15, and the last eye to the sky was at about 9:30. Very, very patient children, very, very patient adults. And we issued lots of cards. I gave little talks, anything to pass the time while they were queuing. But yeah, real success.
Good. Well done. We need to do more of that. Yeah. There's clearly an appetite in Edinburgh for public visual observing, so we need to do more of that. So if that's your thing, let me know. And we do have a little group set up for doing regular public observing, working out how we're going to do it. Obviously, we can't plan for the Scottish weather. Well, we can. We just expect not to do any, and that's the problem with the Scottish weather. But there are ways of working that, so let's try and do more of that. And I believe that was the word of the night.
Yeah, Jim's comment was, I didn't know you could say wow in so many ways.
For members, it is an election year. Terms are now for 2 years. I will be coming to the end of my presidency after 4 years in June. And that's when our AGM is. So we do need people to help. Council member places will be available. Specific posts are also available. So please consider getting involved in that. Please don't assume someone else will do it, because otherwise only a handful of people will be doing everything. So please get involved. We do need your help to keep the society running. We are a society run by members for our members. No one else is going to do it for us. And it isn't difficult to do, and it is good fun, actually. So please do get involved. Over the next few weeks, on Wednesday next week, we have our monthly imaging observing group meeting, and that's for ASC members, and that's a place where we all learn together, and they're really active and really good fun. That's on Zoom, and if you haven't been to one before, then please consider coming along to it, because I think you might find it interesting and enjoyable. On the 21st of February, we have Dr. Daniela Bustamante talking about the First Trillion Observatory. That will be an online-only meeting, so you can see it on Zoom as an ASC member or on YouTube if you're a visitor. The next meeting here will be on the 7th of March, shedding light on the dark side of the universe with gravitational lensing. And it'll be here on Friday night as usual, on Zoom for members and YouTube for visitors. We will have something later on in March which hasn't quite been firmed up yet. We have another Friday meeting here on the 4th of April, and that is a members' night where we will have a number of short talks from our members. So if you've got something you would like to talk about then please let us know, but we're starting to put together the program for that. That's really it from me for now. I'll come back and talk about the sky in February later on, but if I can hand over to Stewart McKechnie now, that'd be great. Sorry? Yeah. There's a little clip on top of this now. There we go, that's on there.
Thank you. My apologies for sitting down. I don't think I'll be able to stand up for the duration, so your indulgence is requested. I've been told that my talks are very boring. So if I nod off, don't be afraid to wake me up. Next slide. Okay. First slide. My interest in astronomy started as a teenager, and Patrick Moore, I bought one of his books and read it and reread it. I wanted a bigger telescope, but they were too expensive, so I ended up making one, which you can see on the screen, 6-inch Newtonian. And I was quite amazed when it actually delivered nice images. Next slide. Coincidentally, my boyhood home was at 10 Observatory Road. My family had nothing to do with the Royal Observatory, which you can see is very close by on Blackford Hill. You see the Braid Hills and Pentlands in the background. The telescope you've just seen would be locked down to a concrete pad in the back garden of that house, boxed. Next slide. These are pictures I took in Albuquerque, New Mexico, using an 8-inch reflector. And what I did to produce them was I pointed at Sirius, which is the brightest star around that evening. And it was low in the sky, 20 degrees elevation. So it was a long atmospheric traverse, a lot of scintillation going on. Once I had the star centered in the picture, I took the eyepiece out and put a CCD camera and focused the camera on the primary mirror. And then what you see are these pictures, which is the light from Sirius as it arrives on the ground. And if you happen to be looking up, you'll be sampling a tiny part of these patterns, which are continually moving and evolving. And if the jet stream's overhead, traveling at 100 miles an hour, the patterns will flip by at that same rate. These are pictures that anyone could produce, should they be interested. Next slide. Over the regions where the wavefronts are relatively smooth, which they are for distances of 5-6 inches, the image that a small telescope will give you is called a Neri pattern. And this is the most perfect image rendition you can have. You can have worse renditions when the atmosphere starts to interfere. But Lord Rayleigh defined his notion of telescope resolution as being able to resolve two stars, binary pair, when the second one exactly overlies the first dark ring of the other star. And when you've got two of them in that juxtaposition, what you actually see is the image on the right. And between the two peaks, there's a 26.5% drop, and that's considered enough to have resolved the binary. A 6-inch, 15-centimeter telescope produces resolution of about 1 arcsecond. If you're not familiar with that measure of angle, the naked eye, unassisted, resolves to about 60 arcseconds. So a 6-inch telescope allows you a 60 times improvement in resolution. Next slide. The images you get with a small telescope are completely different when you use a bigger telescope. The images shown here are from a 2.4 meter telescope. I chose that one because it's the size of Hubble. You see the picture on the left is a full color picture, and you can see it's a short exposure picture. All the speckles and radial streaking are all related to the scintillation patterns we saw a few slides ago. If you put a green filter on, only allow the green to go through, you get the pattern on the right. The radial streaking disappears, but otherwise it's the same. To give a perspective here, the 2.4 Hubble telescope, which doesn't have to worry about the atmosphere, would take all the light that you see in that star image and compress it into the size of a single speckle. And that speckle would be intensely bright. Next slide. I'm going to be talking about my general theory of imaging through the atmosphere a little bit. The previous theory was developed in 1964, and it was called Kolmogorov theory. And it was based, because there was a lack of understanding, on a postulation, namely that the atmosphere is constituted by Kolmogorov turbulence. And it has this Kolmogorov characteristic everywhere in the atmosphere, at all times, all geographical locations, all latitudes, all weather conditions. And the structure sizes are supposed to range from a centimetre at one extreme to tens of kilometres, with all the intermediate scales also present. Now, it was a bit of a wild stab, but the principal developers, Kolmogorov himself, who's a Russian, Tatarsky, Hufnickel and Stanley, and Fried, they were the primary developers. And the ones that are underlined are ones that I've spoken to directly. So I was able to kind of assess where their minds were at on the subject. Particularly the underlying members were ruthlessly promoted Kolmogorov theory. But they didn't just do it by scientific truth and scientific method. It was by deception, misinformation, cajolery, cover-up, and proven instances of falsified atmospheric measurement data and brazen scientific fraud. Now, I'm glad to get that off my chest. I must give the impression I'm some sort of extremist. But we'll try and get rid of that impression by the end of the evening. The consequences of this theory for observational astronomy, ground-based, were catastrophic. In 1975-6, I just completed my PhD in laser speckle. So it gave me a kind of flying start into understanding stellar speckle, the speckle we saw in one of the images earlier. So I was offered a postdoc position, and I chose to work on imaging through the atmosphere where you've got a continuous scattering process that leads to graded images. The general theory requires no postulations about atmospheric properties, Kolmogorov or other. When required, the key atmospheric properties are simply calculated from readily measurable properties of star images. But it can't be the kind of seeing disk images that you saw earlier. It must be of the most general type, which I call core and halo. And you'll see what I mean by that later when I show you pictures. If you only look at the seeing disk image, and that's all you've got to go on, it doesn't give you the complete information portfolio. And so you can come up with all sorts of bogus models that fit at that wavelength, but for all the wrong reasons. But they can't explain the images at any other wavelength. So we'll get to that. Next slide. Kolmogorov theory pessimistically concluded that the best you were going to get from the ground in terms of resolution was about an arc second. In other words, a 6-inch telescope can give you all that Kolmogorov theory tells you is attainable. So that meant you don't need to make your telescopes to particularly high optical precision. It meant cheaper telescopes, and that caught people's attention. And so people from 1965 to 1990 were building a whole series of telescopes, including the British United Kingdom infrared telescope in Hawaii, which happens to be administered by the Royal Observatory, Edinburgh. But the Canada-France telescope, the Mayall telescope in Tucson or Kitt Peak, Arizona, they're all built to shoddy tolerances. And they all produced blurry, uninspiring images. It turns out, in my opinion, and I'll supply the information, the justification for it, that building these a whole generation of telescopes like this was a colossal blunder in retrospect. And it's one that obstructed progress in ground-based observational astronomy for over a quarter of a century, because they were getting images that were pretty lousy, but could have been much, much better had they built better telescopes. Characterizing telescope imaging over atmospheric paths using the new theory. A plane wave that arrives at the top of the atmosphere from a distant star, the light might maybe have traveled for 50 or 100 years. So these waves are, whereas they start off as spherically expanding, by the time they reach Earth, they're completely planar. But once they come down through the turbulent atmosphere, or the inhomogeneous atmosphere, where there's temperature variations, and where it's hot, the air expands and its refractive index lowers, and where it's cold, it thickens and the refractive index increases. That means that certain parts of the wavefront are going faster than others, and the wavefront becomes corrugated. Now, if this were the wavefront arriving at the E-ELT, it doesn't just stop at that. It will be equipped with an adaptive optics system which looks at the corrugations and tries to fix them in real time. And the technique does work, and ideally it should reduce the perturbations to zero. But in reality, it doesn't do that. It maybe gives you a factor of 2 improvement. The angular spreading of the wave, if you allow that to diffract, or if you put a lens there to collect it, bring it to focus, the angular spread at the focus is roughly proportional to the wavefront gradients, because the wave tends to propagate at right angles to the tangent locally. Now, the height fluctuations on the wave we can characterize by the root mean square variation. That gives you one element of the triangle to find out the angles of the slopy part of the waves. The other measure we need is the distance over which the slope subtends. And I call that distance W, as shown in the picture. It's the distance over which, whatever condition the wave is here, at a distance W from there, the wave will be statistically different. The angular spreading is proportional, roughly, to sigma over W. And that basically determines the size of the star image in arc seconds. While doing this postdoc research, I'm now familiar with speckle. I decided to try an experiment and got time at Royal Greenwich Observatory on a 36-inch telescope. I was given a week, and you hope that during that week you may get a couple of clear nights. Sometimes lucky, sometimes aren't. But the telescopes then, as they are now, were on the grounds of Hersamshoe Castle, built with funding from King Henry V for one of his favoured knights that was present at the Battle of Agincourt. The measurements that I took consistently gave much smaller values of sigma and W than supposed by Kolmogorov theory. And I don't mean just smaller by 10% or 20%, smaller by a factor of 10. You know, an enormous difference. If the actual measured values were correct and were representative of observing sites throughout the world, which I didn't know, but if they were, there'd be revolutionary consequences for ground-based observational astronomy. Next slide. This was the experiment that I did. A 36-inch telescope formed a star image, and it fell on an aluminum thin foil with a very tiny hole, pinprick hole in it. So the light dropped through that hole, some red, some green, some blue. It met a neutral density beam splitter, which allowed half to go straight through, and the other half was sent leftwards. And on one leg, you would have a red filter to only allow red through, and the other one, a blue filter, or any combination. And the measurements we took were simultaneous, red and blue pictures 1,000 times a second. And we would sustain the recording for about a minute. So we had 60,000 intensity measurement pairs, which gives us decent statistical precision. And no matter which combination of colors green and blue, green and red, blue and red, whereas the formula, the constants going in were different, they all gave the same value for the root mean square, sigma. And it had to be that way, otherwise there'd be something wrong with the formula that I developed. So it was very intriguing. Next time I was up in Edinburgh, I used to play tennis with Hugh Butler, who was an astronomer in ROE. And his particular interest was twinkling. And I told him that I just measured sigma. And I said, before giving him the answer, I said, what would you think it would be? And his answer was hundreds of wavelengths. And it was way off the mark. But Kolmogorov theory had given birth to crazy notions like this. And some of them were baseless. Next slide. That is the telescope that I used, the 36-inch YAP. You can visit it to this day. Royal Greenwich Observatory moved away, but left all the instruments themselves at Hershmanville. And they're operated by a charitable outfit, the Observatory Science Centre, open to the public, and well worth a visit if you're down in East Sussex. Next slide. Kolmogorov theory expected that there were huge atmospheric structures, as well as smaller ones, and the intermediate. So there's a fundamental difference between large structures in the atmosphere and smaller structures. And just to do a side-per-side comparison, there's two waves shown here. The one in solid line does 10 cycles across the 3-meter baseline. And you'll see that the peak to trough is about 1 micron, as if you read the scale on the left, which is in microns, a 1/millionth of a millionth of a meter. So there's obviously a lot of vertical stretching to show micron type fluctuations. The vertical scale was expanded by 160,000 times to give the images, the waves we've got. Now, the large structure only affords 2 cycles over the 3-meter wave. The smaller structure has 10 cycles, but you'll see that the peak to trough are much smaller, 5 times smaller. And in fact, looking at that firm line, it goes from plus and minus half a micron. There's a total variation of about a micron. Now, on the right, I've shown the 0.55 micron, which is green light. That's the wavelength. And you'll see that it's smaller than the fluctuations caused by the smaller turbulence. It's also much smaller than the fluctuations caused by the larger turbulence. Another bar on the extreme right shows what the infrared wavelength, 2.2 microns, shows its scale. And you'll see that it's longer than the fluctuation for the smaller turbulence, but smaller than the fluctuation in height for the large turbulence. So whether the wavelength is longer or shorter on the wave fluctuations makes quite a difference. And the cause of the difference is diffraction. And the result is that instead of seeing distant images, the images that you'd expect have a much wider, richer variety. And you'll see pictures of them later. Next slide. The figure on the left shows the images that you'd have got if you focused these waves at visible wavelength, green, 0.55 microns, and also the near infrared, 2.2 microns. And you'll see that for the large structure, the longer wavelength has a slightly sharper image, but it's not significantly narrower than the visible image shown in the dark dotted line. Both waves are pretty much, because they're smaller than the wavefront fluctuation heights, they're both very broadly scattered. The picture on the right, which is based on the smaller turbulence, at visible light, we've still got the same sort of image we had with the larger turbulence. And that is because the height fluctuations are much larger than the wavelength. With the 2.2 micron wavelength, that wavelength is longer than the peak to valley of the smaller turbulence waves. And you can see that what happens is that the light is not completely scattered. There's a fraction of it which you can calculate, which is directed into the image that the telescope would have produced with whatever aberrations it might have. Would have produced in the absence of atmosphere. So it's delivered, that part of the image is going to look exactly like the images that the Hubble telescope gives us. Next slide. So I wasn't sure if my maths was correct or if the experiment was done properly. If you're going to step out of line in a major way, you need to be pretty careful. So anyway, in 1975, after getting this result and predicting these sharp cores in the images, I went up to the floor above the optics department, to the astronomy department, where Brian May had just aborted his PhD to make money. I asked them up there if anyone had seen these cores and images, and they said they hadn't. But they said, we also don't look through telescopes. Our charge here is developing instrumentation. So, but they said there was a Roger Griffin at Cambridge that had claimed to see rather odd things, and they directed me to him. So I phoned him up, and when I talked to him, when I mentioned the word core, he said, yes, I see them all the time, but no one believes me. So in February 76, because his observations had 4 distinct characteristics, and all of these 4 were represented in the mathematical analysis, I was pretty confident that this was a real phenomenon to be pursued. So I gave a talk in, it was a conference center right next to Pebble Beach. So my first introduction to America was Pebble Beach, which is a high house price area, very impressive. So what I said during, or at least from the talk abstract, the observations made by Griffin using the Palomar 200-inch, which was the biggest telescope in the world at that time, and the 100-inch Mount Wilson telescope, are in such close agreement with the predictions of the theory, the new theory, that it is almost certain that Griffin has seen cores. By optimizing some of the factors that control the brightness of the core, it may be possible to use this phenomenon as a tool for improving the resolution of large telescopes. David Fried, one of the developers of the older theory, he must have been alerted to this heretical individual McKechnie, because I found that he was the chairman of the talk session. And afterwards, at question time, he flatly rejected the possibility of image cores, dismissing reported sightings such as from Griffin as illusory. So normally when an experiment doesn't suit the theory, you have to go back and check the theory. But with Fried, no, we know the theory's right. So if you're seeing these strange things, there's something wrong with your neurology. Next slide. Before directly challenging Kolmogorov theory, those parts of the new theory that needed more rigorous mathematical development, and I appreciated that. Months of effort in 1977 failed to progress, and I reached a point of exhaustion, had to walk away from it. It took a further 13 years to obtain the desired rigor, by which time I was working in Albuquerque, New Mexico, at the US Air Force Research Laboratory. And once I had that rigor, I started streaming off paper after paper. I was confident now that I was right and they were wrong. This is an excerpt from the talk that I gave in 1990 at the annual meeting, at an SPIE conference meeting. In night seeing conditions at typical telescope sites, The optimum wavelength, that's the one that comes to the sharpest possible focus. And that would be one that contained a core. And you can calculate what that wavelength will be if you know what sigma is. The optimum wavelength is 2 pi times sigma. Very simple. And based on my 0.4 microns measurement of sigma, the optimum wavelength was put in the range 1 to 2.5 microns, just longer than the extreme visible extreme, and into the near IR. In that range, a 5-meter telescope should be able to obtain a resolution of the order 1/20 of an arc second to 0.15 arc seconds. Now, this is certainly putting a foot over the outer line when people are expecting 1 arc second as the normal image size. But it also requires, to get that amount of sharpness, the telescope had to have diffraction limited optics. And that was where we completely broke with Kolmogorov theory, which allowed all sorts of horrific, poor quality optics. 0.5 arc second resolution is roughly the same as obtained by the $2 billion Hubble Space Telescope at visible wavelengths. Publishing this and other radical material could have been career-ending had it been wrong. It didn't end my career, but nowadays I live in suffocating poverty. The Air Force approached me. All right, these cores you're talking about, are they real or imaginary, illusory? We want from you a definitive experiment which will come down one side or the other. So I said, well, there is, and it's not a particularly complicated experiment. They said, what telescope do you want? So I chose the multimillimeter telescope in Arizona. It had 6 mirrors which could be phased up, but one of these mirrors was actually made to perfection. So I thought if they don't succeed with phasing up, at least I'll be able to use the 1.8 meter mirror E. It was a beauty. And what was I going to do with that telescope? Well, point it at a star and capture a series of short exposure, very short exposure images, 1,000th of a second each exposure. And the reason for doing that was that the telescope jitters. There's seismic vibrations induced from the earth below. There's wind swaying the telescope by imperceptible amounts, but when you're dealing with very high magnification, these amounts are magnified. So the stars sort of wandering around in your field of view. By using the short exposures, it basically froze the motion. And I expected to find a core in every single image surrounded by a kind of scattered halo, as it's called. Moreover, if you took all 1,000 pictures and you chose a reference star and recentered all the images to that one, because remember, the stars jumping about your field of view from instant to instant. If you added them all up, having shifted and added them, you should get a very high resolution image of the star. In order to resolve the detail in this high resolution image, instead of using 0.65 arc seconds, which was the pixel spacing used by ROE in Hawaii with the U-Kirk telescope. We cut that down by a factor of 13 to 0.05 arc seconds. So this is the factor 13 is an indication of the sort of resolution improvement that we're looking to get. We also had to tighten the telescope focus by about 10 times because this fine core feature was much more sensitive to focus. The outcome, back one, within a couple of weeks, the two astronomers that were invited to the Air Force labs to hear my pitch had co-phased all 6 mirrors, and they had 0.1 arc second image cores at 2.2 micron wavelength. Even though seeing at visible wavelengths was a mediocre 1.125 arc seconds. These images show, well, the one on the left shows the core and halo image that I anticipated from the Mayall 3.8 meter telescope on Kip Peak, Arizona. And a lot of the light goes into a kind of halo, which I've separated out bottom right. And the other part goes into the core, which is shown in isolation in the top right. And when you add one top the other, you get the full image on the left. So that is roughly what we would expect from the Mayall telescope, according to my version of reality. Next slide. These are pictures taken by Julian Christo with the Mayall telescope. The one on the left is just a standard long exposure image. And this was the time-honored method of imaging stars used by astronomers, you know, up until that point. The image is just a blur patch, about an arc second across. And that's all Kolmogorov theory expected. And certainly the telescopes delivered it. But by using the short exposure images, where each one has the core, and recentering them to take out the telescope motion, you end up with the image on the right. And you can see that you've got a sort of airy pattern, except there's a squareness to it. There's an astigmatic aberration in the telescope. Otherwise, it would have been a nice circular ring like in an airy pattern. The next slide. Same wavelength, 2.2 microns. Long exposure image on the left. It's not obvious what's underlying, but the one on the right is the addition of all the short exposure images suitably shifted. And you can see that although it's a less than half an arc second separation, which you normally wouldn't expect to resolve, it's resolving it with a comfortable margin to spare. Next slide. This image on the top left top is the airy pattern, the shape of the core on the 4-meter Mayall telescope, if there were no aberrations. If there's a quarter of a wave of aberrations, it would look like the one on the top right. Half a wave, bottom left, and one full wave, it completely wipes the core, levels it. You probably wouldn't be able to distinguish it from the halo noise. The state of the optics of the Mayall telescope was such that the core image would look like the one on bottom left. So you can see that with a better telescope, how much improvement there was there to be exploited. Next slide. This was same top images, this sum of 400 shifted and added pictures, where you see the point spread of the telescope. Bottom left is the long exposure image obtained in the standard time-honored manner. And bottom right is a single short exposure where you've got the core superposed in a speckled cloud which constitutes the halo. It kind of breaks up the ring pattern. Next slide. In the summer of 1990, I made my usual visit over to Edinburgh to visit my parents at Observatory Road. And I offered the Royal Observatory to give a talk on what had been going on in Arizona and Albuquerque. The talk took place on August 1st, 1990. Hosted by Mr. E-ELT. And the highlight of the talk was the 0.1 arc-second image cores. These images astonished the ROE astronomers. So they soon organized themselves to see if they could create similar images with the Euclid telescope in Hawaii. And about 6 weeks later, I got an urgent call from Dr. Colin Humphreys that they hadn't managed to get any cores at all, and he couldn't understand it. The problem was the low light bucket, which is the descriptor that they gave to that telescope. It was cheap. It's a light bucket, but it'll deliver everything the atmosphere permits. That was wrong. He hadn't been able to see any cores at all. And the reason was that the optics were just so bad that they were beyond redemption. Next slide. Local newspaper interest in the predictions of the new theory. The science reporter came to my house one Saturday morning, and he had read reports on my theory, and he wrote this half-page article. Looking sharp on Earth, ground-based telescopes can be as good as Hubble, physicist says. He also made some phone interviews with astronomers to get a wider perspective. And he phoned up Dr. Horace Babcock, who had been director of Palomar Observatories from 1964 to 78. That was the apex position in astronomy worldwide. He controlled the largest telescopes. His quote in the paper was, "Bad seeing is caused by the atmosphere. There is no doubt about it. McKechnie simply doesn't know the score." So I wasn't too happy to read this. And from being normally a peace-loving individual, I found myself with all sorts of psychopathic thoughts of violence. Anyway, I got over it after a while. 6 months later, he and I happened to be on the same session within 3 talks of one another. And I knew he was going to be there, so I showed these images. And he was astonished. And he left me with a quote that for him it was something entirely new to my experience. Horace Babcock is the person that credited with inventing adaptive optics. Next one. Within the end of the year, ROE had sourced £650,000 to improve the optics. 8 years later, as a result of the optical upgrades, they're delivering images close to the limit set by the wave nature of light. In fact, at a wavelength of 2 microns, the best U-Kirk images thus far recorded rival those of the Hubble Space Telescope. So it was a risky claim to make in the newspaper, but it was ultimately justified. The crude prior Kolmogorov optical tolerances that had been used had been a blunder on a monumental scale, one that resulted in the gross underperformance of every large telescope built in that quarter-century period. Instead of these telescopes, potentially diffraction-limited 5-meter class telescopes offered more than an order of factor of 10 resolution improvement. In the optimum wavelength, that's 2 pi sigma, if you remember that little formula, which is now accepted in the lexicon of astronomy. They refer to it as the sweet spot wavelength region. Good name for it. I'll skip this one. Here's the E-ELT optics layout. You can see the main primary mirror, 39.3 meters across. I won't discuss all the intermediaries, but the image forms at the Naismith focus. The optical design was carried out by computer ray tracing, which should result in a perfect design if you play around with it. The design should be perfect. Yet, as I found out a year in January when I went down to a meeting on that program, they hadn't factored in diffraction into any of their calculations. And the diffraction from the atmosphere and from the telescope optics, without taking these things into account, one cannot realistically expect to be able to deliver the full potential of that telescope immediately. It will have to be a second phase to get diffraction in, to know what they're dealing with and how best to tweak all the adjustments and the pixel spacings and the magnifications. Next slide. The problem with my theory, the main difficulty, is that there's so many niche areas of physics and mathematics. I won't list them all, but you can see them for yourselves. While individual mathematicians might be familiar with some of them, there's very few, if only one that I know of worldwide, that actually is able to handle all of them. And without being able to get into theory with these branches of mathematics, there's no way you can ascertain whether it's correct or incorrect or what. Most professional astronomers just consider the theory as a mystery, and they know as much about it as I know about relativity theory, which is about nothing, because I haven't been through the math and don't intend to. When I was at an astronomy meeting in Glasgow, a talk given by Dame Jocelyn Bell Burnell, the person who discovered the pulsar. And afterwards I was talking with her, and I said that I had a talk that might interest the Royal Society of Edinburgh about the general theory of imaging through the atmosphere. And she nixed it right away, declaring the subject is far too complicated. So I need to engage with people like that on a deeper level. I mean, that's just an offhand brush away, like, you're an annoying brat, don't bother me. Maxwell came up with his theory of electromagnetic in 1860 roundabout. It was 30 years before people accepted that he was right. And he had to fight the astronomical establishment. The Astronomer Royal, Sir George Airy, thought that Maxwell was barking up the wrong tree, that he should go back to his dynamical models of gear wheels, one representing magnetic field, the other the electric. Anyway, the trouble is that when they finally accepted that Maxwell was right, he'd been dead for 8 years. So I'm trying to avoid that fate myself. Jocelyn Bell Campbell wasn't aware that there was already a book out, and there's been another edition published within the last couple of years, that all of the theory of imaging with big telescopes is laid out. Next slide. I won't waste time. I'm not sure how much longer I've got. Okay, missed this one. Here's a picture of a binary star taken with the Keck 10-meter telescope. I took it off the internet. I just rapidly modeled it through my mapping programs. And it enabled me to characterize the effect of the atmosphere, the telescope optics, the adaptive optics, everything's thrown in the mix. Next slide. And their image was at 1.65 microns. You can see that I've got one that looks somewhat similar, top right. And this is in the sweet spot wavelength range. Obviously, they're going to choose a wavelength in that range for maximum impact. But you can see with the other wavelengths, the visible wavelengths, were dead in the water. That's, is that 20 microns? Bottom right. Although you're getting airy patterns, the wavelength is so long, it's larger than the optical path fluctuations. Airy patterns, sizes are proportional to the wavelength. So when you go along wavelengths, you get airy patterns, but they're huge. Next one. Here, the easiest thing to fix in a telescope are the fixed aberrations. You can tune them out on the fly. So I tuned them out, and here are the images that we get with the Keck 10. And you can see that we're talking about very high resolution. The width of each of these pictures is half an arc second. Next slide. This is a section through these images where you can see that it doesn't bottom out at zero. They're an unsatisfying blurriness about them. Next slide. These are predicted for the 39.3 meter E-ELT. And first of all, notice that the width of these individual pictures isn't half an arc second, it's quarter of an arc second, to better show the resolution that you're getting. At 3 microns, the resolution is 19 milliarc seconds. That's 0.019 arc seconds. You can see the sweet spot. Visible light, we're dead in the water. We need far better wavefront control to resolve that as an area pattern. Next slide. With this one, I fixed up the fixed aberrations of the telescope. It's the easiest thing to do. And you can see that things become a lot sharper. And at the wavelength 1.6.5 microns, the resolution is 10 microarc seconds. Now Betelgeuse, the red giant, in Orion, has an angular subtense of 50 milliarc seconds. So now we're able to resolve 5 different elements across its disk, vertical and horizontal. Next one. These are the sections through these images. You see that there's a nice satisfying zero between them. They really are well. Next one. Actually past to the next one. When I submitted the 0.1 arc second images with the mail to the Optical Society of America, all 3 referees were sued strongly in favor of publication. That didn't satisfy the topical editor. He elected 2 additionals. He worked in Boulder, so did they. The reviews were vehemently opposed, and one contained mathematics showing how Kolmogorov theory could easily explain the images. I checked through the math, he had a square root missing. So that kind of halted his charge. It didn't halt the topical editor. He rejected my paper. Anyway, I phoned up the editor-in-chief and explained the circumstances, and it was published. But it delayed it for two and a half years. Not satisfied with that, I found out who these referees were. One was Tatarsky, the wave propagation lab in Colorado. They published the rebuttal article, still claiming that Kolmogorov theory could explain the images, giving no mathematics, giving nothing, just wordage. And I was asked to reply in the same issue, and I did. But when I read the published version, I found that my electronically submitted reply had bits missing, as though surgically excised, recalling the circumstances of this missing square root. These images we're talking about, 10th arc second, they expose the fiction of Tatarsky's long-held Kolmogorov turbulence postulation, and it's destroyed the foundation of Kolmogorov theory. Meanwhile, in 1994, shortly after the rebuttal article, the Optical Society of America, oblivious to the mortal injury that had just been suffered by Kolmogorov, awarded him the Max Born Prize. Ironically, Max Born was professor at the Mathematical Physics Department of Edinburgh University in the 1930s to the 1950s, and he was a heavyweight. Max Born was the PhD advisor to J. Robert Oppenheimer, and he was the grandfather of Dame Olivia Newton-John, which is even more mind-boggling. He was also the recipient of a letter from Albert Einstein with the line, "God does not play dice with the universe." Next slide. This is one for Freed. In 1990, they chose the wavelength that was going to go into a 747 aircraft a megawatt laser with projection optics that could beam the beam out. And the idea was to destroy theater ballistic missiles at distances up to 400 kilometers. I had just finished my paper, and I looked at the optimum wavelength numbers. And if they had chosen, any wavelength they had chosen would have been better than the one they did choose. They couldn't have made a worse choice. So I started a round of talks going to the Pentagon, Missile Defense Agency, also in Washington, Air Force Research Lab, Boeing, you name it. They didn't know what I was talking about. I got nowhere. So the program started in earnest in 1996, despite my objections. And it completed in 2011, 16-year program. And when the system was tested, it didn't manage to kill these missiles at 400 kilometers, but it did manage to kill them at 15. I mean, to miss your objective by a factor of 25, it's like buying a £250,000 Ferrari and finding it can only do 10 miles an hour. Anyway, that program cost the US taxpayer $6.5 billion. And in my view, it was a heist where, particularly by David Fried, who milked the Air Force out of hundreds of millions of dollars for consultancy, based on dogma rather than hard science. He's passed now. Good riddance. Oh, I had one, this is the last slide. I gave a talk in Seattle, and Tatarsky was in the audience, and he didn't like what I had to say, so he challenged me. And it was a bit vexatious. Anyway, when time was called in that debate, I went and sat down to listen to the other talks. And this elderly gentleman comes by. And I knew who it was right away. It was Professor Charles Townes. And he was well known because he got the Nobel Prize for inventing, or co-inventing, the laser. But he told me, he came by and he said, "I'd like to speak to you. Can we go out to the foyer?" And he said, "I too do not believe that Kolmogorov theory is correct." And unfortunately, at the time, I didn't realize what a monumental force he was in American science. What I hadn't realized was that he was chairman of the US government Science and Technology Advisory Committee for the momentous Apollo moon landing program. I mean, to be chairman of a committee overseeing that program where there's so many branches of science, rocketry, creating atmospheres that men can survive in outer space, I wouldn't have taken the job for a pension. But he took it, managed it, and the rest is history. I could have leveraged his reputation much more than I did, had I been aware of that, if I'd been paying attention. I think that's a good point to wrap up.
Thank you. We're a bit short of time. You've got time for 2 questions?
Oh, yes, sure.
We've got time for 2 questions, maybe. If you'd like to let me know. I'll leave that there for now. Anyone got a... Yeah.
Could you give me
Thanks for that. Just trying to understand what you, the key point about optimum resolution.
Yeah.
when I used to make or try making telescope mirrors a long time ago, you would talk about figuring it to within a quarter of wavelength to
Yes.
to get the optimum. So what in those sort of terms, what are you aiming for with the E-ELT and so on? And
with a
what do you
quarter
say
of
is
a
optimum?
wavelength of aberration,
Yeah.
your ideal area pattern drops in brightness to about 80% of what it could have been.
Yeah.
But that is still very good. And for all practical purposes, if you're within quarter wave, you've got a diffraction limited telescope. The optimum wavelength, that is a wavelength that particularly arises when you've got a very large telescope, when some of the light's in a halo and some of it's in a core. And the longer the wavelength you choose, the more likely you are, more and more light goes into the area pattern. But the trouble is that at the longer wavelengths, the area pattern is growing in size, angular size. If you go to the shorter wavelength region, the core, the area pattern starts diminishing and the light spilled out into the halo. And there's a crossover point where if all of it's in the halo, you get very poor images. If all of it's in the core, you get very poor images. But there's a point somewhere between where the fraction 1 over E, E being the Neperian base of the Neperian logarithm, 2.718. When the core contains 1 over 2.718 of the total light, you get your sharpest possible imaging. Or if it's a laser weapon, you get maximum bang for your buck. And you've only got to beat 15 kilometers, so it's appetizing.
Any other questions? I think there's probably quite a lot of amateurs who, someone here, Jim, a lot of amateurs would like to chat to you about their telescopes and whether they bought the right upgrade to the mirrors or not.
Sure.
Hi. I'm just curious, can you say what the motivation is behind the fraud that was perpetuated?
The fraud by Freed was that when information started coming in about people seeing cores, he couldn't afford to suddenly acknowledge that, oh yeah, I was wrong. There are such things, and it changes the whole scheme of things. He would have lost his apex consultative role with the Pentagon. And with the Pentagon, all you have to do is to schmooze with the colonels and generals, and you only need to read one book page ahead of them in the book of knowledge, and scratch their back, and it becomes a mutual admiration society. And you get a bunch of car salesmen running the show that have no idea about real science. And they're in the highest echelons. And I would think it would be even easier to maintain your position in these echelons now that Trump's in charge, because he's pretty easygoing about most things.
Okay, thanks.
The United States Air Force, don't come after us, you heard it here. Fine. Okay, well, can we thank Stuart again? That was really fascinating.
Thanks, Mark.
Okay, the sky this month, that's a picture of the Sol Nebula, which was taken with our 0.3 meter, not 30 meter telescope in Spain, and that was processed by John Briggs. It'd be nice to have a 30 meter one, but probably too much hard work. So the moon this month, we're just past first quarter, the full moon is approaching, which will blot out all the nice faint objects in the sky for us. It's going to be new moon at the end of the month. We can start imaging again. I'll speak up. There we go. And that's another picture of the moon that we took with the telescope in Spain, processed by John. As you know, I've been doing some live streaming for National Astronomy Week, and that was one of the pictures I took just as the streaming session started, just before the streaming session started, and that was actually in full sunlight, so that was with an infrared pass filter. So the sun was still up, still bright, so you can actually do astronomy during the daytime. And remarkably, the seeing was actually quite good, so you can make out the lunar straight wall there, quite a good detail. And the eyes of Clavius are on view as well. So the two craters poking up out of the shadow at lunar sunrise over Clavius. So the sun, you'll be glad to know, is getting higher in the sky, as it always does at this time of year. Today it reached 19 degrees altitude, and by the end of the month it'll be 27 degrees, so it'll be full summer by the end of the month, hopefully. And the sunrise and sunset chimes changed by about an hour as well, so it'll be rising at 7 o'clock by the end of the month. Robert Arnold hasn't been waiting for the sun to get too much higher, so Robert's on Sky, and he's been imaging the sun, and there it is in white light on the left, and hydrogen alpha on the right, and it's been quite interesting recently. There's been a very interesting sunspot complex, quite a lot of groups within there, which you can see, and it's made up of 30 to 40 dark cores, so it's been really quite interesting, and it's more than almost 500,000 kilometers across, and that puts us into context. You are here. Sadly, there are no I would say no interesting comets. There are no bright comets for us. Douglas will disagree on that one. There are always interesting comets out there. We have been following C2023E2, and Douglas has been updating us on that in the newsletter, and also 2023 Q1. And these were a couple of pictures that have been taken. This is by Robert again. I don't know if you can really make that one out, but it is there in the center, that fuzzy blob. And Q1, Douglas Heady, using our telescope in Spain, has taken that one. That has had an interesting coma shape. It's been a bit of debate about that, and we've been trying to help to settle the arguments on that, but I'm not sure we've come up with any solution on that one. The other one we have been following for quite a while is 29P Schwarzmann-Wachmann one, and it is in outburst again. This is data from the BAA, which we've submitted and we've contributed to. And you can see it is actually quite an active comet and has a number of outbursts. And there has been another one very recently. And that is a picture that we took again in Spain. And it's normally quite fuzzy, around about magnitude 15, 16, 17 even, but it's actually got quite a strong nucleus now. And it is around about magnitude 11. So it's interesting to see how that changes over the year. No major meteor showers this month. Most of the good ones seem to be in the second half of the year. So there's nothing much to see until the Aquariids in April and May. But it is still quite a decent shower. And the later ones, the better ones are later on in August and October and December and so on. That's from the Global Meteor Network. But as you may know, we do have lots of meteor cameras in our society. We've now got 17, and I think another one is on the way. So we'll have 18 shortly, but that is the coverage that we have. So we've pretty much got the whole of the UK covered, got a bit of Germany, and Radim has got Central Europe well and truly covered, one of our members in Slovakia. And you can keep an eye on what we capture every night on our website at the Meteor Cameras page. It's really quite interesting. On a good night, you can see lots of interesting streaks across the stacked images, and you get a time-lapse image as well. And if our meteors are matched with other cameras elsewhere, then we can get quite a lot of information about the meteor, about the height and the speed and the size of it, whether it's going to drop or not, things like that. So keep an eye on that page of the website. Okay, you've heard a lot in the press about the so-called Parade of the Planets. It's been hyped up, telling you things like this is a once in 10 million years or whatever it happens to be, once in a lifetime. well, probably you won't see the exact same combination in your lifetime that we have now, but the parade of the planets is not a once in a lifetime thing. The planets have been around in the sky like this for quite a few weeks now, and they will be for a few weeks more, so don't think you've missed it yet. They are still on display. So we have Venus, which is shining brightly in the southwest, which you can't fail to have missed, really. Uranus you will have missed because it's used a telescope. Jupiter is high in the south, as is Mars. Saturn and Neptune are really getting rather too close to the sun now. You can still just about get Saturn, but it's getting quite hard. So, yes, as I said, Saturn is going to be behind the sun, not literally behind the sun, but in its glare over the next month or so, next few weeks. Venus, though, is a really easy to see, and it gets it to its highest altitude on the 10th of February. And the greatest elongation, the distance west from the sun, is on the 25th of May. So it's minus 4.6, so there's nothing brighter in the sky apart from the moon and the sun, and a pretty decent sized disk of 33 arc seconds, and it's got a phase of about 31%. And it's pretty high at sunset at 33 degrees. And that's a video of a live session I did of Venus showing the atmospheric turbulence. I don't have any adaptive optics, so I can't improve that. I don't know when we will get adaptive optics for amateur telescopes. I think we've had some attempts at it, but it's still quite expensive and not very efficient. I don't want mine ever being deformed anyway. But there's not very much you can get out of Venus, although David Brett has actually managed, using a combination of filters, to get a bit of structure in the clouds, and we can see that, but there are actually some cloud shading. So I never managed to do that, but David's done a great job on that. Jupiter is the star, probably, of the planets. It's really well placed. It's high overhead. Not quite as bright as Venus, but magnitude minus 2.5, and a larger disk in the telescope of 42 arc seconds. Again, that's another video from a live observation. You can just about make out the great red spot there as well, and the belts. But with image stacking, using fast frame rate video, then you can actually process that sort of information out of there. And David, again, has done a great job picking out lots of detail in the belts. And I'll talk a bit more about Jupiter in a minute. So a number of us have been following Jupiter recently in some of the storms that have been happening, as I've been boring you about in the newsletter. So I'll bore you a bit more about it now as well. So these are two images, one on the right obviously in color, and the one on the left in infrared. So that's just a filter that allows just the infrared through, which makes the image slightly steadier for us because it's only dealing with one wavelength going through the atmosphere, or a small amount of wavelengths going through the atmosphere. And this is a little outbreak that we've been following. It started out as just a white dot. It shows up very clearly the infrared image as well. It's been called the NTB outbreak, the North Temperate Belt, I think. As I'll explain later, I think that's possibly wrong. But if you look at it just a couple of weeks later, you can see it's actually left quite a wake of destruction behind it. It's left a track behind it, churning up the atmosphere. We've also been following a storm in the South Equatorial Belt, and that also started off as just a simple white dot, but if you look at what it's actually done now, it's actually churned up the whole of the South Equatorial Belt quite dramatically, and from something that looked at just a bright white spot. That's actually very interesting to have been monitoring in the last few months. That was in November, I think that was first discovered. These sorts of turbulences can actually affect Jupiter dramatically. So here are a couple of pictures, one from 2009 on the left, where Hubble took that. And if you look at a year later, the South Equatorial Belt has almost totally disappeared. These sorts of storms can do that. It did come back later on, but Jupiter just didn't look like itself for quite some time. So who knows what's going to happen with the current storms? Maybe it will actually do the same thing. Maybe it'll do something completely different. We really don't know, but it's fascinating to monitor it. As I said, it's been called the North Temperate Belt, the NTB outbreak, but if you look at that, I think this is possibly the North Tropical Zone where the storm actually is. There's the equatorial belt, the main band at the top, and the little white spot is actually in the North Tropical Zone, I think. The temperate belt is actually a thin, darker line above that, and I don't think that's where the storm is, so maybe we should be calling this an NTZ outbreak, not an NTB one. Mars is also well placed at high in the sky, altitude 60 degrees, minus 0.7, not quite as bright again as Jupiter, but very obviously orange and coloured. Quite small through the telescope, 13.5 arc seconds. In 2020, it was much more interesting because it was much larger and we had a really good apparition then. But we can still get details out of it. So there again is a video of it that I took. You can see the white patch of the top, the North Polar Hood, and you can process that out and get a little bit more detail. David Brett's gone quite a lot further, and I've got a really nice image of Mars there with a larger telescope that will give you extra resolution. And I think you can actually see, if you can make it out, a lighter patch there, which is probably some morning clouds over the Elysium region. So Mars is still worth looking at, but you have to work quite hard because it is quite small. Okay, looking at the stars. So this is looking south at the middle of the month, around about 9 o'clock in the evening. So there's our parade of planets, Venus, Uranus, Jupiter, and Mars, going in a line around about the ecliptic. High in the south is the well-known winter constellation of Orion, and it's useful as pointers to other things in the night sky. So, as usual, following the belt up, we get to the red star Aldebaran, which looks very like Mars, only a little bit fainter. And carrying on from there, we get to the Pleiades star cluster. And that's this picture by Eros from Edinburgh. And Pleiades, Seven Sisters, Subaru, whatever you want to call it, relatively local at 444 light years away. And lots of hot young stars in there. If you carry on following the belt of the stars downwards, we come to the brightest star in the sky, which is Sirius. That is a very local star, only 8.6 light years away. And just above it, a star Procyon, which seems to be all by itself, never seems to be associated with anything, and it's the brightest star in Canis Minor. Again, another local star, only 11.5 light years away. High up, again in the south, we have the constellation of Auriga, which I think should get a lot more attention, but I'm not giving it much more attention tonight. But lots of star clusters in there, open clusters, and interesting nebulae, which we images like to specialize in. To the left, we have the two stars, Castor and Pollux in Gemini, which is normally easy to pick out, but I've seen people recently who are actually slightly confused because the two stars are joined by a third one, making up a triangle, which is the planet Mars. So it's actually slightly confusing not seeing the twins as we normally do. And in there is a well-known star cluster, M35, and that's by Ian Smith. With this one, you get a bonus smaller cluster as well, NGC 2158. And this one was called a shoe buckle cluster, which Ian put in his note, which I'd never heard of before. Less local at 3,000 light years away, but still relatively local. To the left of Gemini, we have the very indistinct constellation of Cancer. None of the stars in there are particularly bright, but it does have a well-known cluster, M44. And that's by Nigel, which is sometimes called the beehive, Pricepe, which means the manger. And again, that's pretty local at 600 light years away. There is another cluster in Cancer, which I think is slightly more interesting, which is M67. And that is sometimes known as King Cobra Goldeneye. I don't know if anyone else had heard that. I certainly hadn't, but I don't know who does the naming. Well, we've tried to name some things, we know that. But it is actually more compact and slightly more interesting. And of course, we've got Leo rising in the east with this interesting set of galaxies, but I won't talk about that this month. We'll probably mention that next month. Finally, looking north, we have the summer triangle stars of Deneb in Cygnus, and Vega and Lyra are actually trying to go below the horizon but failing, and they are both circumpolar, so you can still see the summer stars if you're longing after the warmth of summer as they get below the pole, but they will not actually set as seen from Edinburgh. Rising in the west, in the east, as I said, we have the galaxies in Leo, and also the large clusters in Coma Berenices, which we'll talk about over the next few months, I'm sure, but it will become galaxy season in the Society, so I expect to see more images of galaxies. The well-known asterism of the Plough, part of Ursa Major, is also getting higher, and it is already galaxy season for that because we have some very interesting galaxies in there. M81 and 82, and 101, and then 51, which is, strictly speaking, in the neighboring constellation of Canis Venatici. And here are a few pictures of that. This was taken with our telescope in Spain, M81 by Eros. Not so local, so we're on quite a different scale now. So we're talking 12 million light years away rather than just a few hundred or a few thousand now. So it's quite a different distance scale. And here is the Whirlpool galaxy, which is actually two interacting galaxies. And that's 24 million light years away. And that one's by Mike Christie from our Zero data. There is another one which you may not know about, called the Hidden Galaxy, IC342, 11 million light years away. And that is a very interesting target. It's actually been quite difficult to image for most amateurs, and when I've ever imaged it, it's been much fainter than that. But from Spain, we've actually managed to gather lots of data, and John has brought out the detail in that. The reason it's called a hidden galaxy is it's lying behind all the dusty areas of our galactic equator, so it does actually make it quite difficult. But if it wasn't for that, it would actually be a very dramatic galaxy, because it's 29 arc minutes across, which is about the same size as the full moon, and would be magnitude 9, so it would actually be quite a dramatic galaxy for us to see. And of course, all of that northern sky rotates around the pole, which Ian has nicely done there, using our data, using the Dorada telescope in Spain that we have as well. So, very nice picture. And that's it from me, unless that asteroid does hit us, which it will in about 10 years' time, is it? 1.3%, so don't go digging your bunker just yet. Thank you. That's it for tonight, unless anyone has any other comments or anything. We have tea and coffee at the back. Please do hang around and have a chat. Introduce yourself to people if you're a visitor, and hopefully we'll see you again at a future meeting.